This is what happens when you try to snap a photo in low light. Instead of a crisp memory, you get a muddy, shifting texture of grain and static. That grain comes from thermal fluctuations and tiny electronic glitches inside the camera's hardware. As the internal components heat up, they misread the incoming light, creating random variations in the pixel values. Image processors call this sensor noise. The environment outside the lens adds its own layer of interference. Stray light fluctuations and microscopic dust particles scatter the signal before it ever hits the sensor. Then, the camera has to translate that continuous analog light wave into a rigid digital format. This conversion causes tiny discrepancies, known as quantization noise. And when you send that file over a cellular network, compression algorithms and packet loss introduce even more errors. By the time the shutter closes, the raw data is already riddled with physical and digital interference. From the exact millisecond of capture, every digital image is an inherently flawed, mathematically chaotic file. A grainy sunset photo on a smartphone is an annoyance, but in high-stakes environments, that same static is a critical failure. Medical imaging machines rely on clear scans to detect microscopic anomalies, and self-driving cars need perfect visibility to read road signs through a heavy storm. If a computer's vision is clouded by digital interference, it cannot distinguish a pedestrian from a shadow. It has to see the true physical shapes beneath the static to make a safe decision. To fix this, computers run an invisible mathematical process called spatial filtering. It is a method of calculating surrounding pixel values to clean and repair the broken physical world, frame by frame. A computer sees a photograph as a grid of numbers. Each pixel's value dictates its brightness. To fix errors, the computer uses a kernel, a 3x3 matrix that slides across the image pixel by pixel in a process called convolution. As it slides, the kernel acts as a linear filter. Filters like the mean or Gaussian calculate the average of the surrounding numbers inside that 3x3 square. If one pixel has a radically high, noisy value compared to its neighbors, the averaging process flattens that spike down to match the rest of the group. By systematically averaging these extreme values across the grid, the computer turns a chaotic, grainy patch into a visually smooth, clean area. Averaging the numbers removes the static, but it also blurs the details. To preserve the hard edges of physical objects, the computer needs a completely different mathematical tool. This diagram shows the Sobel Operator. The 3x3 matrix on the right hunts for boundaries in the image grid. It calculates sudden numerical jumps between neighboring pixels. Detecting a rapid change, like jumping from 100 to 200, definitively maps the boundary. But algorithms also face a different threat, known as salt and pepper noise. These are completely maxed out or dead pixels that act as extreme anomalies. Regular averaging would simply smear this error across the image. To deal with this, the computer runs a median filter. Rather than averaging, it ranks neighboring pixels from lowest to highest. It isolates the extreme outlier, ejects it entirely, and replaces it with the group's median value. By alternating through this specialized toolkit of sliding matrices, computers selectively heal dead pixels, smooth out thermal static, and sharpen the boundaries of reality. When you pull back from the microscopic numbers, the sheer scale of this math becomes apparent. These algorithms execute those calculations across millions of pixels simultaneously, sweeping over the entire frame in milliseconds. This exact convolution process runs instantly in your pocket. Every time you tap the shutter on your smartphone, your processor slides thousands of invisible kernels across the sensor data to give you a clean photograph. These hidden matrices operate continuously across our digital infrastructure. They run inside Instagram's compression servers, they clarify the scans inside modern hospital diagnostic machines, and they clean the feeds of global satellite arrays monitoring the Earth. We operate in a physically and digitally noisy universe, surrounded by stray light and thermal interference. Beneath our screens, an invisible army of sliding matrices constantly processes that chaos, mathematically correcting the static to show us a clear, unbroken picture of the world.